This conference will now be recorded.
Okay, so over to you, Bruce.
Thank you very much. Hope I'm coming through loud and clear from my home here in Bristol. Obviously, if the internet gives up for some reason, I hope somebody will point that out to me in some way, because I don't get a lot of feedback here talking to the screen. Anyway, here goes. Let's assume it's all working. So I'm going to talk about ultrasonic manipulation and its application across the length scales, and it's a kind of a personal view on this subject. Let me just put these things up here. So I'm going to first of all introduce the topic by way of kind of a brief history. Then I'm going to talk about this idea of the length scales that these forces operate on. I'm going to tell you a bit about the forces, and then I'm going to tell you about two what I call force devices. They're devices that I've been the worker on, and my group has, and we've got a lot of use out of them. So they've delivered a lot. So I'm very pleased with the way they've gone. And then we're going to move on to talk about dexterity. And as it says there, I'm thinking there of the ability of acoustic manipulators to perform skilled operations and tasks. If you look at the dictionary definition of dexterity, it talks about doing things with your hands, but I'm going to talk about doing them with ultrasonics, and I'm going to introduce the idea of an ultrasonic robot there, and then we'll finish by talking about future applications, although as the talk goes on, a number of applications will be mentioned. Okay, so here's the sweep of history and a few of the key papers. Like a lot in acoustics, things started, I guess, with Lord Rayleigh. He's important for this topic because he defined the acoustic radiation force, and so he was the first person to write down an expression for it, which we'll see in a bit. Actually, others had observed the effects, most famously in something called Kunst's tube, where the air is forced to vibrate and dust is seen to form a series of lines on the nodes. A very famous experiment, but Lord Rayleigh did the first kind of mathematical description of that, and then there are a whole series of other people that have contributed to this. You'll see at the top I've written acoustic tweezers, and I'm going to probably switch between acoustic manipulation and acoustic tweezers as I talk, and to me they kind of mean more or less the same thing, so please excuse me there. But I'm not going to go into detail about the history. I did want though to talk about two kind of events I think that are particularly important for this field. So the first is the advent of space applications. So in the mid 1980s, NASA invested quite a lot of money and research effort in using ultrasound and ultrasonic radiation forces to trap and hold objects for applications in space. And so there they were trying to hold things, whatever they were interested in, still in space, whilst the space station moved a little bit, and they didn't want the things they were trying to hold, which were all sorts of experiments, where they wanted to hold things in a contactless way, were floating around in space. And so not only did NASA do a lot of work on that themselves, but various universities associated with them also did work. And so as it's shown there was a bit of an explosion in interest in these space applications. And so that really kick-started the field. Before that, it was a kind of a niche area, so a bit of maths had been done, but it was those space applications that caused the field to take off and the technology to develop further. The other thing more recently in and about the 2000s was the advent of lab-on-a-chip systems. And so at the bottom there is a few examples of what I mean by lab-on-a-chip systems, so microscale systems, usually operating at megahertz with wavelengths significantly below a millimetre, in the hundreds of micrometers in size. So the idea of shrinking the lab down and doing a whole range of different operations that you'd normally need masses of equipment to do, but doing it on something like a chip, not a silicon chip, but well, it could be made of silicon, but not a silicon chip in an electronic sense, but a microfluidic chip where there was flow, and then the acoustic side of it was you could apply, and there's still a lot of work on this to, continuing. You can apply forces on these microscale objects in these microscale devices, so shrink the lab down onto a chip. So that all took off in about the early 2000s, and as I said, it's still a really active stream of work today. So yeah, you can see the bottom right-hand picture is a state-of-the-art chip produced last year. I can't quite remember what that one does, but it looks like it's doing some sort of filtering operation. So those are the two kind of, I think, key things that have happened over the history that have led to where we are at the moment. So that's the kind of background. So the next big thing to think about when we're doing manipulation is the length scale. So you saw the term tweezers that I used earlier, and so we all know what tweezers are. We use them quite a bit, and they've got a set of tips that grab things, and the size of the tips of the tweezer are the things that determine kind of what we can do with those tweezers. And so it's these length scales, which ultimately end up being the wavelength of the sound, that are our ultrasonic tweezer tips here. So anyway, there's a length scale going from nanostructures and below on the left-hand side to what I call macrostructures, but larger scale, centimetre scale objects on the right-hand side. And so the point I would like to make here is about the idea that it's been the advent of various bits of technology developed for other purposes that have led to the unlocking of various bits of this length scale here. So if we think about, I think two of the most important from my perspective are a piece of piezoelectric material of various sorts, little piezoelectric discs that lots of you will have played with, and you'll have many of them in your labs, probably not so many in your homes, but they give you access to frequencies from say 1 to 100 megahertz. It's the typical kind of range where that thickness, that frequency is determined by materials. They can go a bit higher than that, they can go a bit lower than that, but that's the broad range. And usually they're operated in their standard form into a coupling liquid of some description. And so in that liquid, so let's think about water here, that's giving you access to length scales between 15 microns for the 100 megahertz signals and 1.5 millimeters for the 1 megahertz signals. So that's one bit of technology that gives you access to a really wide range of length scales on the right-hand side of that graph. Another key bit of technology is these 40 kilohertz devices, which are very prevalent, designed first for use in parking sensors, for measuring the distance between your car and a wall or a person, but also used in security devices to detect the presence of intruders. 40 kilohertz is chosen because it's well above the audible range, which typically is 20 kilohertz, so you're twice that, so there's no chance of a human being able to hear these things. But it's not so high that the attenuation in the air limits how far the waves can go, and that gives you a wavelength of a bit over 8 millimeters. So that's the technology that I'm talking about here. That gives you access to manipulating things at the smaller end cells and individual cells, then microorganisms as well. Come back to that as well. That's a little C. elegans worm. And then larger scale objects like an insect there of some description, and small electronic components at the macrostructures end, so millimeter to a centimeter kind of range. So that's where we are at the moment with this technology. That's not to say it couldn't go further in either direction. Another technology that's very much related is that of optical tweezers. They've been around for quite a long time, really, before, or certainly the technology is far more developed than acoustic tweezers, although when were they actually developed? Probably a similar time, I guess, but they've been used far more, and relatively recently, a couple of years ago, Arthur Ashkin won a share in the Nobel Prize for the early development of optical tweezers. So really, really significant technology. And you can see they are giving you access to a smaller length scale, because the typical wavelength that's used is the order of a micron. So that gives you access to, again, to cells, but also things significantly below cells. So if I press the next button, you can see some of the things that have been manipulated there, down to cold atoms on the one hand at the really low wavelength, low size regime, objects within cells, and cells themselves. And so the kind of the overlap region is the cell. So which is great because there's a whole load of applications for manipulation of cells. And what, you know, one of the most famous things done with optical tweezers has been grabbing, there are two tagged beads, you're pulling a strand of DNA, that's what's shown in the middle there, and you can measure the stiffness of a strand of DNA there. So someone's got their microphone on out there. It'd be good if you could just check that you're muted, please. Okay, so they're two different bits of technology giving you access to different bits of that length scale. And the point I was trying to end there with was talking about cells being an area where both optical tweezers and acoustic tweezers give us access, which is really important because it's such a big application area. Okay, so now a bit of detail about the forces. Sorry for the equation, but I'm kind of assuming quite a lot. There's not going to be many equations in this talk, but I'm assuming that most of you are acousticians. And anyway, even if you're not, I'm going to talk about these at a level where I think most engineers and scientists would be able to understand. But along the top there are all, so imagine a particle of some sort in an acoustic field. What are the forces that that particle sees? They're kind of listed across the top there. There's this gradient force, which I'm going to talk about in a minute. There's the scattering force, that's the kind of pushing force that takes the particle in the same direction that the waves are propagating. There's the force due to absorption, so if energy is drawn into the particle, then that momentum is passed to the particle. There's then also a streaming force, so the acoustic waves transfer the energy to the particle, but also to the host fluid. And if the host fluid moves, and that's the stream, then the particle will be drawn along. Depending on the relative size of the wavelength and the particle and its acoustic properties as well, one or another of those forces can dominate. But, okay, so that's a very general picture, but it turns out that in many of the cases that we're interested in, so say manipulating many cells in a water-like medium or manipulating pretty much anything in air, anything small in air, then we end up being in the Rayleigh regime. So I think this is the most practically important regime that these acoustic devices are working in, and that's when the particle size, A, is significantly smaller than the wavelength, and then it's this gradient force that dominates the scene, and that's sort of shown by those equations below. So if you look down towards the bottom of the equations, there's a U parameter, which is this so-called Gorkov potential, and that's the thing that determines this energy landscape, and then the force is the gradient of this energy landscape. So that's kind of all you need to know about it really, other than what are the parameters that affect the magnitude of this force. So if you look along here, you'll see it's a to the power 3, a cubed. So that's the size of the particle, and because it's cubed, it ends up, you can think about it as a volume effect. So the volume of the particle is really rather critical. And then if you look along that equation, you'll see an F1 acting on P pressure and an F2 acting on V, the particle velocity. And then if you look below there, the definitions of the F1 and F2, and so F1 concerns this kappa down there, which is a compressibility, so it's something to do with the stiffness of the particle, and F2 concerns the rho, which is to do with the density of the particles. So they're the three key things: the size of the particle, the compressibility or stiffness of the particle, and the density of the particle. And it's not just the particle, it's the particle relative to the host fluid, which typically in this talk is either water or air. I'll try and remember to highlight when I'm talking about which one of those. So that's this Rayleigh regime where the particle is small compared to the wavelength. That said, the easiest regime in a way to explain is the opposite end of the spectrum, the Ray, as it says, optics or acoustics regime, because this explanation applies equally well to light as it does to sound. So on the left-hand side there is a picture of a light example, courtesy of Wikipedia, and you can see a red kind of intensity plot going across in these two beams here, with a centrally located particle here and a particle off to one side here. So if we look at the particle off to one side, you'll see there's a thick ray going vertically up called ray 2, which is refracted, and basically it's being refracted off to the left-hand side. So energy, and therefore momentum, is being pushed out to the left-hand side, and therefore there's a reaction force pushing the particle over to the right-hand side back towards the center. So the tendency in this optical system is for particles to be drawn to the high intensity regions. Exactly the same argument can be used in acoustics, and this is a picture from a paper I wrote in 2016 showing really exactly the same thing. Hasn't made it into Wikipedia yet, but nonetheless, if you want to read it in that paper, there it is. But it's not, I wasn't the first person to comment on this. It's a well-known phenomena here. And if you look at on the bottom there is the intensity profile. It's this thing in this kind of grey-blue thing, and this H1, H ray just above it is the high intensity ray. That's refracting energy over to the right-hand side this time, and therefore there's a reaction force back towards the left, towards the high intensity of the sound bit. But there's a really crucial difference between how the optical system works and the acoustic system works here, which is really highlighted in the next slide. And that is, for most of the common systems that we're interested in, so for example, trying to trap a polystyrene particle, reference plastic particle in water, which is it's used as a polystyrene is used as a reference because it's somewhat cell-like in its properties, both acoustic and optical. So this the same would go for cell in water, and the same would also go for most particles that can be manipulated in air as well. So in the case of the light, the refractive index, the contrast of refractive index is the crucial bit. And in general, for the things you'd want to manipulate, like cells in water, the refractive index of the particle is higher than that of the host. And that results in things being drawn to the focus, as I just mentioned. Now, in acoustics, the things you want to manipulate generally are stiffer and more dense than the host. So imagine the cell stiffer and more dense than the surrounding fluid. And in that case, actually the effect is flipped around the other way, or the sign on the effect. And so things are not attracted to foci, to high intensity regions. They're pushed away from high intensity regions. So if we go back one slide to that picture on the right hand side, so in that picture on the right hand side, I've shown the very uncommon scenario where the thing you're trying to manipulate has a slower speed of sound to the host media. That can happen on occasion, like fat globules in water, but it's quite a rare thing to happen. So although there is a point where exactly the same thing happens, sound versus light, in general, it's the other way around for sound. So when we're trying to trap things with sound, acoustics, ultrasonics, things end up being pushed away from the high intensity regions. And so we need patterns somewhat like shown here. There's a high intensity ring pushing things in from all sides into a low intensity central region, which is the node, or the zero acoustic pressure region in this case. So that's a key difference worth noting. So when we're trying to generate acoustic patterns for manipulation, we're generally trying to create nodes surrounded by high intensity regions in 1D, 2D, or 3D. So 3D equivalent would be a point surrounded by a high intensity sphere. That's the sort of thing we're trying to create acoustically. So that's very, very general here. Another very general and I think quite interesting bit of analysis is, well, to answer this question, how much force do these waves apply to objects? So here's this really the most basic calculation you can do on this, and it's rather beautiful because it applies equally to light and sound. So if we have a wave of an intensity I coming in from the left with a particular speed c, hitting a perfectly reflecting surface of a particular area, but from intensity, which is per meter squared, to power, which doesn't have a meter squared in there. But I'm sort of assuming that the wavelength is small compared to the size of my perfectly reflecting surface here. If all of that's true, then the radiation force, the force pushing that reflective surface back, is 2 times the incident power over the speed of whatever the wave is, be it light or sound. So that's a really, really, really simple equation that we can use to do back of the envelope calculations. And so if we do that, so there's that equation again, if we do that for a typical, quite a high power laser system actually, we find out that the power that an optical tweezer can exert on a particle is of the order of nanonewtons for some pretty reasonable high power systems there. Arguably, it's often slightly less than that. If we think about a water-based manipulator, here are some parameters: 200 kilopascals, and it's a 100 micron particle, so a relatively big particle there. Then we find that equates to 0.4 milliwatts falling over the particle, because it's the amount of intensity that falls over the particle that's the only bit that can impart momentum to the particle. That ends up giving us several orders of magnitude more force. So here we have micronewtons of force. And if we then think about an in-air case, we can't generate such quite high power. So this is a typical power that we might be able to generate in a reasonable acoustic system. A kilopascal over a 2 millimeter particle, that ends up being 8 milliwatts falling over the particle, leading with the speed of sound in air to the order of 10 to the minus 5 newtons, so tens of microwatts. Obviously, those answers are entirely dependent on the parameters that you put in, but I've chosen some reasonable parameters there so you can sort of see the difference. So on the surface of it, you might have thought you'd get 10 to the 5 times benefit by using acoustics, because that's the ratio of the speed of light to the speed of sound. Actually, because of practical considerations, you end up with getting maybe 3 or 4 orders of magnitude improvement, which is still quite beneficial. But I stress that's only for those examples chosen there. If we look at that with a bit more precision, here is now a graph of force on the particle against frequency. And there are two, to be more precise, I have to envisage particular waves that I'm dealing with here. So shown in blue and red there are a traveling wave, so it's just a plain traveling wave interacting with the object, and then in red a standing wave, so 2 plane waves propagating in opposite directions. And you'll see a few things. One is you'll see the force due to the standing wave is significantly higher, particularly at the low frequency end, than that due to the traveling wave. And so that's telling us that this gradient force that I mentioned at the beginning is often higher than the scattering force, and that's why the scattering force due to a traveling wave is often neglected in practical devices. So, but you can also see that as the frequency goes up, both of those two force profiles tend to some kind of value. And if I press the next button, you'll see that value that they're tending to is that back of the envelope calculation I showed a moment ago. So that really simple calculation is telling us a kind of an upper limit on the amount of force that an acoustic device, or if you wanted to an optical device as well, could apply to a particular particle. The other things on here are, so that line, the vertical line towards the left-hand side, is the line that marks approximately where you might have thought of as the Rayleigh regime, so a particle being a tenth of a wavelength in size, say. I think that was what I chose there. And so you can see that actually it's only towards the left-hand side of that graph that I'm in that Rayleigh regime. And then the rest of it, I'm in an intermediate regime or a high-frequency Ray-like regime. But an awful lot of what's done practically is done in that Rayleigh regime. So here I'm talking about manipulating a relatively big particle, a 100 micron particle. And so looking at that graph, that would lead me to say I need wavelengths in the hundreds of kilohertz to megahertz region for that particular manipulation task in water. Obviously, those numbers change as you change the system. And to complete the picture, if you were trying to use optical tweezers, there would be the optical force line. So for that particular scenario, the acoustic tweezer, the picture does change though if the particle is somewhat smaller than that. Right, so that's about how much force these devices can apply. So now I'm going to talk about these workhorse devices. So first of all, something called a single axis acoustic levitator operating in air, one of my favorites. So these have been around for a long time to hold objects. I talked about the space applications, but there are lots of containerless processing applications used to take high precision X-ray measurements or synchrotron measurements, shown on the left-hand side there. On the right-hand side is what's the typical transducer that would be used to do those measurements, a Langevin horn made up of an assembly of piezoelectric elements clamped together with a backing mass on either side. So the whole thing moves as a mass, as two masses, with the piezoelectric elements being the spring. This whole thing is kind of doing that, causing the front surface to vibrate dramatically, outputting high intensity sound, and therefore using it to levitate things. And so that was kind of like the state of the art when we started thinking about doing things a different way. We were thinking about doing things in a different way because we worked for many years with a company called Ultrahaptics, or now they're called Ultraleap, that make ultrasound haptic feedback systems. And they use these things that I showed earlier, these things that derive from parking sensors or motion sensors. And so each one of them by themselves is not as powerful as a Laurens van Horn that you could make, but they're very cheap, the order of £1 or euro each. And so you can assemble a load of them at relatively low cost. And because they've been mass produced, they are very repeatable. And that's critical because they need to be coherent to each other. We need to be able to carefully control the phase of one with respect to another. Anyway, you can do that, and you can put them into devices like Tinylev, as shown there, where, and that's a genuine photograph of the Tinylev in operation, trapping a large droplet of water and a whole load of other beads around it. If you look on the right-hand side, you'll see what the acoustic field in Tinylev looks like. It's a series of high intensity, low intensity, high intensity, low intensity regions there. And the particles are trapped on the low intensity regions, and they're pushed into those traps by high intensity regions. What you can't see there is the much weaker lateral force that keeps them centrally aligned there. We need a strong force to overcome gravity, obviously, otherwise it's not levitation. So we have a strong vertical force, but we do need a lateral force, otherwise the whole thing would be unstable and things would flop about from side to side. But we showed that you could make one of these things at a relatively low cost out of pretty simple parts. The beautiful thing about operating at 40 kilohertz is that although we're above the audible range, a lot of electronics designed for audio work can still be used, and a lot of that's been made and refined over the years. It's available at pretty low costs, so you can buy amplifiers for £5 and controllers for £10 and assemble them into your own Tinylev if you care to do so. And we published some instructions, and if you want to you can't be bothered to buy all the parts separately, you can contact this company. I receive, nor any of my co-authors receive any royalties for this because we just published it, we made it open, but you can buy all the parts in a kit form from maker fabs at the very reasonable price of $70. How long it would take to get to you in the lockdown, I don't know. But yes, that's the peril of doing things open access, that once you've published instructions on how to make these things, then they're completely freely available to anyone. That's brilliant because it means lots of people can do it, but it means that someone can do things very, very cool like this and make some money off the back of your idea. But I got to just say, anyway, good luck to them. So that's a bit about the capability, about what it can levitate. Let's skip over that, I think. But just to say that there are a whole series of people that have, and that's one of the great things about doing open access stuff, that have picked up on these designs and used them for all sorts of purposes, some of which are listed there, characterizing radar systems. A lot of them are, so that's the one of them. There's a lot of them, though, are classic containerless processing applications like evaporation driven self-assembly. So you want to, you're using the fact the particle is shrinking to the droplet is shrink, the liquid droplet is shrinking, but it's got nanoparticles in it, and you're using that shrinking to force the assembly process. It's just one of a number of applications that this Tinylev thing has been used for, all done with nothing to do with any of the authors really, apart from in some cases we provide them with a bit of advice and assistance. The exception actually being the bottom right-hand one, of which Azir Marzo was involved in that work for particle transport systems. Another piece of work that we've been involved in is taking this device a bit further, is something called an Acoustophoretic display, where phoresis is movement, so it just means, Acoustophoretic just means movement with acoustics. And here, it's not a static system, so those previous systems, we feed a particular phase profile into this array, and that's fixed. And usually it's very simple. It might be all the transducers at the top or bottom are in phase with each other. That's the simplest one. or maybe half of them are in phase with, and the other half are out of phase with some reference signal. Whereas here, and this is the direction that we'll talk about in a bit, they're all wired up individually, and so we have access to the phase and amplitude of each of the emitters, so we can control the force field much more accurately. And so in the Acoustophoretic display, we are forming a trap, so this series of nodes and antinodes, just like I showed a moment ago, but moving that around in space very quickly. The idea is to do it so quickly that like the old cathode ray type TV sets worked, persistence of vision makes you think that the object is occupying all those places in space simultaneously. So at the moment, the state of the art, and as well as ourselves, which is Fushimi et al., there's a group in Sussex that have published a very similar device pretty much simultaneously. So the state of the art is we can do relatively simple graphics in real time, but more complicated things like this rendering of a stop sign takes the order of a number of seconds. But you know, it's potentially quite an interesting way of getting a genuine volumetric display that would look, you could view it from all sides and it would look like what it's intended to look like. So it would be like a genuine manifestation of a hologram, but it's not a hologram in the sense that we think of when we talk about holography, but it is a volumetric display that could be viewable. It physically seem like it's there, and indeed it does seem like it's there, but you know, if you try to touch it, of course, you'd destroy the field, the acoustic field, and the whole thing would fall apart. But you can look at it perfectly okay from all directions. So anyway, that's the workhorse type device one. Moving to something at the end now that is not a workhorse, very much work in development. The other workhorse device that I want to talk about is something I call an in-plane manipulator, and this is operating in water, and we're targeting here things like cell manipulation, and you'll see some of the other applications. And to do that, we're operating at much higher frequencies. Here's a picture of the classic device. Again, it's super simple. It's been refined over the years. Something I'm very much a believer in is the devices don't necessarily start simple, but as each generation goes by, you try to make the devices simpler and simple, to strip them down to their essence of being, and then you're left with something that's as well engineered as you can possibly make it. So you can see here we have 4 emitters, so that they're arranged in a square pattern, a central manipulation chamber here, and we're operating at somewhere between 6 and 7 megahertz, giving us wavelengths of the order of well, it says there 220 micrometers in size. And we're exciting with relatively low voltages, 4 to 10 volts. So the ancillary equipment, although it's a bit more sophisticated here because we're in the megahertz region, it's not that expensive a type of equipment here. But we don't, because we're in the megahertz region, we can't just use audio stuff anymore. So the cost of these sorts of things definitely goes up by at least an order of magnitude here. So whereas Tinylev type things, you're talking at the moment of less than £100, here we'd be talking off the shelf parts anyway of the order of £1,000. But there's nothing inherently expensive about the equipment. It's just that it's a rarer frequency range to use. Not so rare if you're like me, a professor of ultrasonics, but rare in terms of applications as yet. But I think that it's interesting. There's a lot of potential for the cost of these devices to go down because there's nothing intrinsically expensive about the parts. Anyway, within that chamber, we form another standing wave pattern. There's one shown, a series of stripes. It can be switched from horizontal or vertical, although typically this thing would be in plane. And in general, with a device like that, I'm thinking about it being slotted under a microscope. So it's in the classic observation plane of your cover slides in a microscope. And that's what happens if you excite all transducers together. You get this egg box-like pattern of nodes and antinodes. And is that going to play? Whoops. No, it's not going to play, but that's then a picture of some objects trapped. There's a video of a picture. We'll come back to many images like that, so it's not critical that that video doesn't play. So if we go on to the next picture, there is a video that does play. I don't know how well it's playing over this webinar, but there's a pattern of these nodes arranged in a grid pattern. On the right hand side, we're performing a chemical reaction within this acoustic field. So it's a coactivation reaction, but it's more or less a polymerization reaction. And so what's happening is, as it starts, this reaction is starting, and we're forming these little droplets, which are all being pushed into these nodal positions where they coalesce into bigger objects. And so it goes on until the only thing we've got left is these droplets in this grid pattern. And so the droplet is a liquid-based gel-like droplet in water. So that's what we're looking at. We're looking at water-based droplets in water here, but it's a genuinely bound droplet due to this coactivation reaction. So it's all held together. And it's a nice system to work with. And this work has been done in collaboration with Stephen Mann, Avinash, Patil, and Langfei, Tian in our Department of Chemistry here. So this is one of their favorite systems. But prior to us using ultrasound, these reactions would happen much more randomly. So the size of these droplets would be, some would be big, some would be small, some would be touching, some would be far apart, and there would be no control of them. But now this is a platform that they can create these droplets in a much more controllable way. And this all happens very quickly and with very low cost apparatus. This is one of the things they've done with this system recently. So here we have, you can now see the whole of the array. The previous picture was a zoom in on a region of it. So here we see a much bigger region. And so we have these coactivate droplets there, these gel-like droplets, which they've sequestered various chemicals. I'm not going to go into detail of the chemistry here, but we then release two reagents from the left-hand side and the right-hand side. And if I press that, you'll start to see the effect of these chemical wavefronts coming from the left and right and transforming, well, what you can see is it transforms the physical structure of these droplets. Sometimes they expand, sometimes they're growing up and then falling over, and then other times they form a shell with a bubble in the middle. So this was from my chemistry colleagues, a very powerful demonstration of the value of this system, because the starting point is a very controllable point. The particles, the droplets aren't touching each other. They're all very uniform in size. And so something like this just wouldn't be possible with the kind of randomized patterns they had previously. And the thrust of that particular group in chemistry is to look at these really simple systems and to try and link those really simple chemical systems to life itself. And so this is an example of going from something really simple into some complexity in a very simple and controlled way. So the end point there, we have 4 or 5 different morphologies, different structures of, with the addition of just 2 chemical reagents. So it's not exactly stem cells turning into different types of tissue, but it's a really simple analogous system which can help people understand those kinds of questions about how life itself started. Just some pictures of those. Some other applications of this kind of system. Top left there, some work of James Armstrong at Imperial College and all sorts of other people, including myself, patterning cells in hydrogels, and showing you can get better formed muscle fibers through an ultrasonic system. We've done some work here at the top right there with the Heart Institute, where we've put down patterns of different cells. So you pattern, in this case, the green cells, and then shift the phases and pattern the red cells. So that's the sort of thing you can do. A beautiful piece of work here by a group in Glasgow, where they patterned Schwann cells, which are cells that guide neural development. So then you put this blob in the middle in position B, from which neurons start to grow, and they follow the patterned Schwann cell. So it's showing you can use ultrasound guide the direction of neurites. So potentially a very powerful way of growing the new nerve fibers. Ultimately, that's the ultimate application. Tremendously exciting potential. So, from the workhorse device has done a lot of exciting things there. And then some more recent work where we've deformed particles in those same sort of systems, but I'll need to move on, I think. So now I want to talk about this idea of ultrasonic particle manipulation being a form of robotics. So this is a debate that I'm going to sort of have with myself here. So the first question we have to ask is, what is a robot? Well, here's the definition from Wikipedia as to what a robot is. It's a machine, especially one programmable by a computer, capable of carrying out complex actions. Well, my judgment is what I've shown you doesn't quite fulfill that yet. A robot can be guided by an external control device, or the control may be embedded within it. I mean, there's a bit of that in what I've said, but I don't think we're quite hitting that yet. We'll come back to this question at the end. Robots may be constructed on the lines of a human form, but most robots are machines designed to perform a task with no regard to their aesthetics. Well, that's a nothing statement, so we definitely adhere to that. Okay, but one of the things I think we need to have in order for us to claim that we've got something like an ultrasonic robot is dexterity. So I'm going to now go through the different elements of dexterity. As I mentioned earlier, that's shown by this this picture here as an example of one form of direct dexterity, holding multiple objects, for example. And so a lot of this was inspired by optical tweezers, which I mentioned right at the beginning and a number of times since. And one of the things that really opened up the possibilities with optical tweezers is the use of a spatial light modulator, which is basically a type of system that can control it's like it's a reflective that can be transmissive actually as well. It's like a lens that you can control its form. So as shown in that picture, a laser beam falls upon this SLM, and the reflected beam then has a pattern that's been determined by this SLM. So they're also used in overhead projectors to create the pictures that you see and to control them. But what you can use them for here is to create a particularly refined pattern of light and dark shapes. So if you look at the end of this, coming out of the microscope objective, as shown there, is 3 traps. So whereas with a simple set of lenses, it's dead easy to create one trap, with something like an SLM where you can craft the optical field on demand, you can create multiple traps and you can move them dynamically. So this is a kind of an inspiration called. Sorry, you just go back a moment. Well, anyway, it looks like we can only go forward for the moment. It's a delay. Sorry. You'll notice that this optical device is called the Holographic Optical Tweezer, or HOT. I wanted to draw that to your attention because the device that Azir Marzo and myself put together is now the acoustic equivalent, the Holographic Acoustic Tweezer, or HAT. And there's a picture of it. Now, there's one thing that's kind of brilliant news from an acoustic perspective. Because the speed of sound is so much slower than light, getting coherent sources is relatively easy. So we can do it with essentially a phased array. So is all we need, what we need in order to create this hat is a load of emitters and a load of control channels feeding into those emitters, which we can control. And so that's the thing on the left-hand side there, a multi-channel coherent source. And so if you can put those things together, then you get something that you could claim is a hat, holographic acoustic tweezer. And if we show it now, run these 2 videos, again, I don't know how well they're projecting through GoToMeetings, but you can see we're doing, on the left-hand side, we can see some optical manipulation, and on the right, we can see acoustic, a very similar thing happening acoustically. The length scales, though, as I mentioned at the beginning, are very different. So whereas the optical case, we're at micron scale of objects, and for the demonstration on the right-hand side, we're at 1 millimetre size objects. That was using these 40 kilohertz devices. So how does that work? Well, behind it, to get it to work in real time, has to be an algorithm. And so a lot of the work went into the development of the algorithm, and one of the key things to getting that to work is defining these traps. What does this tweezer itself actually look like? And so here's some pictures of that. If you want to create a focus, it's just one point. That's that black circle. If you want to create one of these, we call them twin traps, one of these regions where there's two high intensities next to each other, then you need two of these control points spaced by an appropriate manner, and you can then adjust these 2 points in 3D space. So you can define where these control points are. If you want to create a vortex, and we're going to be talking about vortexes in a minute briefly, you need to create a circle of control points and have a phased ramp between them. So those control points are rather important because they feed into this algorithm that we use to create the required field. So just going through that quickly, there's an iterative scheme whereby we in a simulator propagate the waves from the emitters to the control points. Then we have to select what control points we have. So in this case, 2 of them to create the twin trap. We set the phases and normalize the amplitudes, and then map them back to the transducers themselves. And then we iterate around that cycle, and the result of that tells us what phases that we need to feed into the transducers in order to create that trap in that location. To do one trap is actually relatively easy. We don't even need the iterative scheme, but to do lots of traps and to keep them equisized, that's where you really need this iterative scheme. And so if we do that, there are 2 ways of operating it. One is against a reflective surface. I'll just show you hopefully I'll just show you the result. There are a series of particles. Again, they're roughly a millimetre in size. Got a bit of lag on the system here. I'll just press. There's some particles levitated against the surface there. What we're doing to do that, you'll see the video is moving. We just got a bit of, the timing is a bit off here. These videos, it's working now. Okay, beautiful. Well, it's working on my screen anyway. Hopefully you'll see these particles dancing around. If you don't, please look at the original paper, and you can download and have a look at the videos at leisure. We're creating a series of foci here, actually, and we're relying on the fact that where you create a foci near a surface, a focus near a surface, you get a reflected wave from the surface, which interferes with the incident wave, creating a node, a local node, and then we're manipulating those around as you see. So this is quite a simple case, because it's a case where it seems a bit like the optical system, really, that we can use a focus to trap particles. There's a picture showing the foci, and this is just saying that we are inevitably limited by the wavelength, by diffraction, so we can't get 2 individual traps too close to each other before they blur into one, suck the particles into each other. I mean, that's as yet unsolved problem, that it's relatively easy to get particles to approach one another. It's much harder to split them apart. Now, this next one is a 3D version of that. It's working a bit more fluidly on my computer here, which is a bit of a relief. So we've got this 3D shape. We're moving. This is shown in real time, moving these things around, quite a lot of them, using that algorithm. So when you see the particles doing that, it all looks deceptively simple. It's worth having a look at what the acoustic field looks like. And so if you look on the left, that's a group of 6 particles trapped roughly in a circular pattern. But on the right-hand side is showing some of the inner workings of this. It's a simulation, but the reality looks very much like this, showing what the acoustic field looks like and what the phases are on the different transducers. So you can see that we have to have really proper control of the phases. That's what all the different colors represent, different phases. But you can see that our acoustic field pure and clean as the left-hand picture might lead you to think. So the trap region is relatively spread out, particularly in the vertical direction here, and so that tells you that those traps could interfere with each other. There's a lot of ghost artifacts, as they're called, lots of other things that we have generated that are really just kind of noise in the system, really. And so now, what do you tell from that? Well, you can see that this is a non-trivial task, hopefully, but it also maybe highlights why we solve it as an iterative problem to try and get the optimal pattern here. It also tells you that for this particular system, if you try to get the particles to approach each other closely in a vertical direction, that'll be much more problematic than horizontal. Okay, anyway, let's move to the next. This is an implementation of a similar thing underwater and in plane. So it's a bit like whereas what I've just shown you is essentially an extension of the Tinylev kind of in-air system. This is an extension of that workhorse device underwater. So whereas in that workhorse device we had 4 of the transducers and we could only create relatively simple acoustic field, here we have 64 of them and we create much more complex fields. But for this in-plane device, there's a particular challenge which I'm just going to talk about momentarily, and that's that. So if you look at that picture in the bottom left corner there, you can see we're putting all this energy into this circular chamber, and the most obvious thing you might have thought would happen then is we get resonances of that chamber, and indeed, if you don't do something about it, that's exactly what happens. So the key thing to allow this kind of in-plane manipulator to work is to stop these reflections and to stop the possibility of setting up a resonance in there. And so as sketched out there, that's how we do it. If I go to the next slide, you'll see a closer view as to what the boundaries of that device look like. So on the left-hand side is the device, water. In the middle there, you'll see the piezoelectric material, PZT. Crucially, there's a matching layer, which means we get very efficient transfer of energy from the water to the piezo. And then behind the piezo, there's an absorber, which is perfectly matched to the piezoelectric material. So the idea is that any energy incident from the device side goes efficiently through the matching layer and into the absorber where it's dissipated. And that basically means that this device operates as if we have a boundary that's completely dissipative or absorbing. Which enables you to do all the kind of manipulations that I was talking about with the hat device. So that's the key way into these in-plane devices, this control of the boundary condition. So I mean, putting all those things together, the other thing you've got to be doing if you're dexterous is complex movements. Here's somebody's threading a needle, something that's going on with a bit more regularity in my household due to lockdown. But we can do some element of this with the acoustic, with the hat device. So here, in order to grab the thread and the thing you're trying to thread, you have to put handles on them. So that's what those white things are. There are little polystyrene, expanded polystyrene spheres. They're the things that we're grabbing, and then the thread that itself is held up with those tags. I mentioned a bit about creating angular momentum, so that can be done. So you can spin things. It's an important functionality. Just going to move over that a bit and go through these elements of dexterity a bit more quickly here. So the other thing that's important in dexterity is the ability to grab things of different sizes and shapes here, as exemplified by the elephant and the mouse here. To grab bigger things, one route into that is through these vortices. I talked very, very briefly about them, but we have a field where the acoustic wavefronts are spinning, and they've got this lovely attribute that if you spin them faster, the central core of the vortex opens up, and that's been it had been around for a while, been suggested as a route for trapping larger objects. But if you actually try to do that experimentally, you can create these fields, but the faster you spin the vortex, you end up inherently imparting that momentum also to the object you trap. And that then creates an instability, and typically the object just flies away. So we created this concept of virtual vortices, or vortices without this angular momentum. And really that picture in front of you there shows the kind of concept that you rotate for a brief period of time the vortex in one direction, and then for a brief period of time the vortex in the other direction. You switch rapidly, and if you switch quickly enough, then the particle just sees a kind of an average of those two effects. So you get the intensity, the effect of the intensity pattern, which gives you the forces that you want, but you don't get this rotation component, which is the thing that destabilizes the motion. So that was quite an interesting concept and opened up a number of things. Not only the main objective here was to trap and manipulate objects larger than the wavelength, which I think the next video shows, but the other thing that it opened up was this idea of time domain multiplexing. So switching the acoustic field. So whilst previously we'd been limited to a continuous wave kind of system, here we realized that if you switch the system between different states, you can get interesting new states emerging. If we look at the, oh, sorry, oh, where are we? Jumped in. Got to see the video. Or do we? How long do I pause before I think that's not working? Well, as the title dramatically says, oops, where are we? That did show the levitation of the world's most powerful tractor beam, the largest object levitated. Again, I think I'm going to press on because the videos aren't working terribly well, and I don't want to lean on it. If you look at the paper that was highlighted there, if you didn't have time to note it, I can definitely send it to you. You'll see the associated videos. We levitate a particle that's bigger than a wavelength. So the final attribute I wanted to talk about in terms of dexterity, though, is the manipulation of things of different shapes. And so here, let me get the next one. So, oops. So I've got a rather nasty lag between when I press the forward button. Right, here we go. That's the picture I want. So this shows the idea, and it's really a kind of an extension of what I was talking about with the virtual vortex a minute ago. We have these two states. So we're now inside one of these Tinylev type devices. So in air, 40 kilohertz, 8 millimeters wavelength. On the left-hand side is the kind of classic image that we would get if we drove it with the top and bottom out of phase, but all the top elements in phase with each other and all the bottom elements in phase with each other. So we get a bit of focusing, but for the trapping perspective, what we get is a series of nodes, antinodes. So we get very high forces in the Z direction, not much force in the X direction is indicated there, and no ability no control in what would be the XY plane, the kind of plane that you can't see in that projection. Another really quite simple way of driving the same device is something called a twin trap, whereby we split it differently. We split it kind of left for right and drive one side of the array, the left-hand side, entirely out of phase with the right-hand side. And then you end up with this central vertical line of low intensity. So that system there provides a very high lateral force in X, but a much weaker force in Z. So you've got these two different states, pretty simple states, both of them, but that have very different force patterns. So taking the idea of the virtual vortex and switching between these states quickly, let's gloss over, that's just a bit more information about different states. Switching between these things quickly, you need the so shown on the left-hand side is the vertical force. So the standing wave one, the normal one with the high vertical force, you need that in order to levitate the particle. But then on the right-hand side, you can get this asymmetry depending on the way in which you split the top array. So you get you get two things there. You get an ability to control the forces in X, Y, and Z basically, but to change them as well. And so particularly in the XY plane, so which is the horizontal plane, so you can apply more force, say, in X than Y. And so that can be used then to stabilize asymmetric objects. So here are some still pictures, so you can't tell that the objects are stably trapped. But here we're switching between these two patterns, using the standing wave one to keep them vertically levitated and the twin trap to apply a force that is asymmetric in this horizontal plane. So it gives the particle the asymmetric particle a particular orientation, which we can change as well if we want to. I don't know whether this will work, but it looks good on my screen. This is the video showing that they are reasonably stably trapped here, which is convinces me looking at my screen. But and so this is quite an important graph then, which is kind of all of that compressed into a single graph here. So there are kind of two things going on here. We're wanting to apply enough force to levitate something, and so if you look now at the kind of orange line, and then so size of the object is getting bigger. So the bottom axis, horizontal axis, is the object getting bigger from 1/10 of a wavelength to 1/2 a wavelength. And as we go to the bigger object, so the force per unit volume drops off. So we're applying more force as it gets bigger, but we're just not applying so much. And so we're only just, we start to struggle to levitate it at all as we get to bigger objects. We need a more powerful system. So that's the levitation bit. But then system giving a high vertical force, and this twin trap giving us some control in the other plane. So we're applying a torque to the system because of that asymmetry of the force field, and that torque is highest when the particle is biggest, because it becomes comparable to the wavelength eventually, and there's very clearly a different force between the different facets of the cube, say, and as the particle gets smaller and smaller, we see that difference in force between the faces decreases, and so we apply less torque. Anyway, those are the two competing effects, and in the middle, though, is a stable region where we can both levitate the particle and also apply a torque, torque being necessary to stabilize the object. So that was quite an interesting finding about how you trap and hold asymmetric objects. Right, so now I'm going to just conclude with a few slides where I talk about possible future applications. So everything I've talked about really so far has been work that's been done, and you can read all about it in the various papers if you wish. Now it's a bit more about what might happen in the future and how might these things be used. You can see I talked about the workhorse devices which are already being used. Their uses are definitely going to expand, but here I want to think just briefly about the usage of the more dexterous devices. So one thing which is my own personal dream, I'd like to see kind of one of these devices attached to every microscope out there. So I think there's a huge kind of general purpose microscopy application here where microscopy goes from being a one-way process where you look at things and you say, oh, how interesting that is, to a state where at will you can move and manipulate objects. And that could be done potentially at a relatively low cost with an acoustic system. Obviously, such a system would be much more effective on larger objects, and so things like this. This is an example of some already performed manipulation of a small worm. That's the kind of an object that is just a perfect object to be manipulated acoustically because of the size that it is. But objects bigger than that or smaller than that could also be manipulated. So that's one kind of big application area, I think. Another one is arbitrary patterned systems. So this is building on the second workhorse device that I mentioned, where we're creating arrays, and so arrays of what you best I think of as microreactor arrays. So the current system can only do regular patterns. So you can, if you want a grid pattern, you can do that. But if you want an arbitrary pattern, at the moment, there's no way into that. You need the ability to tailor the acoustic field in order to do that. And if you can do that, you can create these patterns which look beautiful, but they would allow you to study in immense detail cell-cell interactions or cells with chemicals. So that could be useful for drug discovery. And I suspect a whole load of things, uses of this type of microreactor array that I haven't yet contemplated even. So that's another big application area, patterning of these micro arrays. Another one, and a very appealing one, is microassembly and fabrications. There are lots of small things out there, and in general, there's a trend for things to get yet smaller. And so how do you assemble these things? There's obviously robotic systems, physical robots, but I think the types of capability that I've been talking about here also lend themselves to manipulating and positioning small things. This is a beautiful piece of work using a holographic technique where Kai Meldon and colleagues in Max Planck Institute use an acoustic hologram, which creates a fixed pattern, and you can see there, you see the high intensity pattern of a bicycle, and the particles were forced to follow the pattern of the bicycle. But I think that's just a tiny window in the huge range of possibilities that there could be for acoustics in microfabrication of all sorts, and that applies to tissue engineering applications, so assembling live things as much as it does to assembling inanimate objects like microelectronics, etc. Okay, so getting very near the end. Is it a robot? I asked earlier, and there were my definitions of a robot. So it's a machine, especially one programmable by a computer, capable of carrying out complex operations. Well, we did that, didn't we? That was dexterity. So we definitely can tick that. It's guided by an external control device, or the control would be embedded within it. So I described the algorithm that we were using to do that control. So we've achieved that. And we know that the last one is a trivial one anyway, because it just says it would help if it looked like a human, but it doesn't have to. So you can't help but fail to make that one there. So the conclusion is that the ultrasonic robots are coming. And with that, I'll thank you very, very much for listening. And I hope there might be some questions for you to answer. Somehow.
Thank you, Bruce. I think there's one question on the chat.
How do I get the chat? Right. There's a question here, a very pertinent question. Is there any possibility of transmitting viruses via ultrasonic? I think that's something we probably wouldn't want to do. It's certainly possible to study cells and small things at a microscopic scale, but I think you'd be talking about small amounts of them in a safe environment. I mean, what I've been talking about has been a kind of a general purpose tool, so it could be applied to all sorts of biomedical applications to grip and move all sorts of things. I think if you're talking about manipulating such things in air, that would be challenging. I mean, there's an interesting, I can't remember now who I was talking to, but about the interesting concept of a sort of an ultrasonic force field that might stop the spread of viruses. So imagine your next generation of PPE, your face mask doesn't somewhat speculative PPE here, I hasten to add, is an ultrasonic force field that pushes viruses or whatever air particles away. I got to admit, that was a rather tongue-in-cheek conversation. Thank you very much. Rather tongue-in-cheek conversation. I mean, I think there's no sort of laws of physics that stop such a thing from happening, but I think we're a long way from it being a reality. Are there any other questions that anyone would like to add? Well, it seems not for the time being, unless I...
There's a couple more on the chat, I think.
Oh, they're coming through.
Yeah.
Well, okay, there's a very good question about does ultrasound damage the material being transported, and that's something that's a really important a really important aspect to be careful about. A lot of these things can be made so they don't damage the cells or the tissue, the clusters of cells, but equally, if they're used, if care isn't taken, then they can damage materials. What looks like it, so I think it's good news though overall, in that myself and my team and lots of other teams have manipulated cells, microorganisms, without damaging them. So the good news is it is definitely possible to do that. But I know equally, you can use ultrasound to cause cavitation. You can pierce small holes in objects. You can use it for destroying tumors. So it's all a question of what is the amplitude and what is the local absorption of the ultrasound. Because cells are all different, biological media are all different, you can make a general statement like I've just made, but you then would need to assess these things on a case-by-case basis to be really sure for a particular application that it's safe. So that is a good point for something like the general purpose microscopic manipulator kind of concept, that if that is going to be used widely, then it would have to be shown to not harm a wide variety of objects. So that's one of the many reasons why it's going to take a few years to develop that system. There's then another question here from Stephen. Hopes I'm doing well. Well, I am doing well, thank you, as well as can be expected. I'm sure we're all doing our best under these difficult times. How stable can you get the particle during levitation is the question. And in general, it should be possible to get it very stable. I mean, the systems underwater are particularly stable because there's the surrounding water imparts high drag on the particles, so there's a lot of the viscous effect of the water is enough, and because the particles that you're trying to manipulate, the cells, are reasonably small, those water-based systems are really very stable. In air, things do have, when you do the in-air manipulation, things do have a tendency to wobble around a bit. I don't, and I think that comes often from external air currents and also from heating effects, small heating effects, because the emitters can heat up and create convection currents. We've recently been doing quite a lot of work, as you saw, on the Acoustophoretic display, where we're moving a particle around very quickly, and in order to do that, we had to really carefully calibrate one of the ultrasonic systems, and that was a painstaking and laborious process, but we did manage to do it, and so there we got very good control over the stability. But those experiments were also done in an area where we controlled the airflow very carefully. So I think there's no reason why the ultrasonic forces can't be very stable, as long as you control it. So it's not the strongest gripping force, so you just have to carefully control the other forces that might be brought to bear on the particle. And then on the other side, of course, the stronger you can make the acoustic force, the more force, and therefore the more stable the system would be. So that's but you don't necessarily want to always max out on the force, because that brings with it other negative things like increased streaming or increased heating. So there's quite a delicate balancing act there that I don't think anyone knows exactly what the answer is to that question. Well, their questions are coming in thick and fast now. What was that one there? Going at them in order. User-controlled interfaces. So I suppose he's saying reply in private. Well, I'll just briefly say that that we haven't, that we've been concentrating more on the physics than on the user interface side of things, but there are other groups working on that. I can supply more detail on them in private. Let me look at the next question. Limitations for speed. Well, I think there the thing to look at there would be to look at the work on these Acoustophoretic displays. So if you haven't got those references, do look at those. Those are so the one from ourselves. Fushimi is the first author, and the one from the group of University of Sussex. There we've moved things very fast. So I think those papers are the fastest people have ever moved things. What exactly limits why things can't move faster? At the moment, from our perspective, the work that we did, the biggest limiting factor were the transducers themselves. Because if you try to change the phase on the transducer really quickly, the transducer can't keep up with that demand. So we've in our system, we found the transducers were limiting. That's not a fundamental limit in physics. So new developments in transducers could get over that obstacle. But that's for the device we made, that was the current practical limit. Not electronics, not software, not algorithms, but the physical transducers themselves. Another question here. There's a question about extremely small particles. I think that's a good point, and there are other theories which I haven't gone into here, which apply for really small particles. I think we'd need another talk to go into that. But yeah, although the Gorkov force applies, to the very small particles, there starts to be other forces, asymmetric drift forces. It's just a name, but it's another force that starts to dominate at smaller and smaller particles. So that would be a difficult question. It's a good question about the really small particles and really high frequencies, but one that's hard to answer here. A question about cloaking, which seems slightly left field, but oh, he's saying reply in private as well. But I will just mention briefly the fact that I think it was about 5 years ago we wrote up a piece of work where we created an ultrasonic crystal. So we trapped particles in a 3D grid. So you saw the 2D version done in collaboration with my chemistry colleagues in Bristol, but we did a 3D version of that as well, and then we passed a different frequency sound through that ultrasonically generated crystal, and yeah, it was quite a fun piece of work. We showed we could reconfigure that crystal, so change the lattice spacing. So that wasn't quite a coordinate transform to do cloaking, but it was a little bit of a hint in that direction. The next question seems to be the same question again, I think. Okay, so I go on to the next one about the precision. What affects the precision? So I think I've mentioned, in air, I think the biggest things are any other reason why the air is caused to move. That flow of the air is then has a knock-on effect on pushing the particles. So we found we got much better results by going into a room with more controlled airflow, or very little airflow, just enough to be able to breathe and no more. But what other effects? There are environmental sounds. Usually the amplitude of environmental sounds is too low to, the acoustic force. There is a force due to environmental sounds, but the force associated with them is very low, so I don't think that's an effect. Nearby electromagnetic waves, we've not noticed that's a problem either. I think ground fields, whilst they might pick up on sensitive measurement equipment like microphones or electromagnetic sensors, they're sufficiently low that the force associated with them is low. I mean, that's something that I suppose if you go right back to the beginning of my talk, and I talked about these forces, the forces we're applying are of the order of, whatever they were, micronewtons or nanonewtons. That force, if you think about a wave of having a particular amplitude where it applies a force, an oscillating force, So this force that I'm talking about is a steady state force that exists over, if you time average this field. So if it was purely oscillating, this force wouldn't exist. It's only happening due to nonlinear effects, basically. But what I wanted to say was, if you compare the amplitude of this force compared to the amplitude of the oscillating force is of the order of 1,000 times greater than this nonlinear force, this radiation force. So that, or really strong light in order to impart these effects. So usually environmental things are not a problem. Right, so some really good questions there. Thank you very much. No more questions for the time being. We're getting near the end of the allotted time as well. I very much enjoyed giving the talk. It's a slightly strange experience because it's very one way. I'm talking to my monitor here, but I hope I'm sure there were, because I could see from the questions, people out there listening. And all right, there's another question here coming in about software for modeling the acoustic systems. I mean, the philosophy from me and my team is always to try and use the simplest modeling tools we possibly can. So we write a lot of it ourselves in MATLAB when we can. It mentions in this question particularly microfluidic devices, and in a microfluidic devices you find quite often boundaries are very important. The exact size and shape and location of them are very important, and that's quite hard to analyze with the sort of simple MATLAB based models that we tend to use. So there we would go to pretty much straight away to something like COMSOL, a finite element package that's very good at coping with all of those acoustic interactions, and would include the elasticity of the surrounding material, the viscosity of the fluids, and everything. But it's a bit of a I guess that's our approach. On the one hand, really try and, if we possibly can, use the more simple kind of models where you decompose the fields into point sources or plane waves. But when they break down, don't try and push them too far, and then we tend to flip the other way and go to finite element methods, of which I think COMSOL is probably our favorite, but other packages are available. Okay, are there any more questions? Well, thank you for saying the talk was clear. That's good. That was my intention. As I said, it's quite a strange experience, because it's really hard to tell if people are listening and indeed what you even heard. So it sounds like the sound quality was good, and the pictures came through, which is brilliant. I'm absolutely delighted. So probably it's time to sign off, I think.
Thank you, Bruce. Yeah, I'll send the recording to Charlotte, who will be able to circulate it to everyone and people who might have missed it.
Great. Well, thank you. I mean, it's nice to have. I mean, it's nice to have the thanks at the end. Very much appreciated. Thank you for listening, everybody. It's been a treat. It's a strange time for all of us, isn't it? Being shut at home, and so thank you for listening. I've enjoyed going to other people's talks, so thank you very much for going to coming to mine. Look forward to meeting you all face to face. Hey, David Lines is out there. Fantastic. Hi, Dave. Good. Right. On that note, I'll remain here for another couple of minutes, but I'll stop talking at this point.
Okay. Thank you, and I'll stop recording. Thanks, everyone.